Hello and welcome to Module 5 of Mechanics of Deformable Bodies. We will be talking about axial deformation in this module. So let's kick off the module with St. Venant's principle. Before that, uh, since you already have the copy of this module, I believe and I trust that you already read this, and we will just be going over the key points in these sections that we will be tackling in this video. So moving on to Saint Venant's principle. So Saint Venant's principle is basically uh, based off the observation that localized effects disappeared at some distance from points of load of application. From points of load application rather. Furthermore, he observed that the phenomenon was independent of the distribution of applied load as long as the resultant forces were equipollent or statically equivalent. So this idea is known as Saint Venant's principle and is widely used in engineering. So what does that mean? Basically, what that means is imagine a bar loaded as such. Uh, it basically says that at certain distances from the point of application, there will be changes in the stress concentration. That is to say that the stress is not uniform across the cross-sectional area. But as you grow farther and farther away from the point of application, the stress becomes uniform, and it looks something like this. The stress distribution rather. So at a distance a, so very close to the top, you can see that it's very the stress concentration is very high, uh, where the load is concentrated, right? As you go farther in, the concentrations, the slopes of the stress concentration or the of the distribution become flatter and flatter, right? So here's at B, and then here's at C, and then here's at D, or finally it is uniform. All right. So that is basically the point of Saint Venant's principle. So this comparison shows that localized effects caused by a load tend to vanish. Okay, tend to vanish as the distance from the load increases. Okay, and this is where we will be capitalizing our study of axial deformation. All right, so uh, this Saint Venant's principle is very important when it comes to stress concentrations, or say if you're designing a support for a certain material, or um, you're designing a beam with a hole through it. There are certain provisions that you have to follow uh, with respect to the hole in between the beam, right? Because there are such things as stress concentrations that occur, and that is why when we see a when there is a seismic activity happening, we commonly see the corners of the openings of the windows and the door. That is where the cracks start, right? Because of the fact that there are stress concentrations at that point. Okay, so we'll be delving into stress concentrations in a later module, but let's leave this at that for the moment. Okay, so let's move on to deformations in actually loaded bars. So basically, we already went over this when we were talking about Hooke's law, but here we are formalizing the the formula for it, and we see that it's still based off of Hooke's law, right? Stress is equal to modulus of elasticity times the strain. Okay, and then from that, we have force over area times length over uh, times total length over modulus of elasticity. Or if you want to make this into a mnemonic, you can write this down as P L over A E, or simply play. Okay, so This is a method for you to memorize the formulas. I don't recommend it. I always want to go back to why the formula is like that. But say you want to apply the formula and you forget, then there's always this other there's always this other way. As engineers, it is our job to uh, develop our problem solving skills, and sometimes it requires more than one method of solving problems. All right, so this is one method of uh, recalling the formula. Okay, so moving on. Equation M5-1 may only be used if the axial member is homogeneous, meaning the member is consisting of only one material. Prismatic, meaning it has a uniform cross-sectional area, and then has a constant internal force, or it's loaded only by forces at its ends. Now, if the member is subjected to axial loads at intermediate points, or if it consists of various cross-sectional areas or materials, the axial member must be divided into segments that satisfy the three requirements just listed. Okay, so an example of this would be here. All right, so this is a compound axial member where we have one, two, three segments and only one force applied to it here. One force here, one force here, one force here. Sorry. Okay, so uh, basically what this means is you have to break this down into segments, because every segment has its own internal force that where it is constant, so that we can apply equation 5 m5-1 based on these precedents. Okay, so we have we carry out the method of sections per segment so that we can expose the internal force, and then applying equilibrium equation, since this is assumed to be in equilibrium, we can determine the internal force that we will be using in the calculation of the deformation. And the total deformation would be the deformation here plus the deformation here plus the deformation here, which is shown here in equation M5-2. Okay, so it's just the sum of all deformations of each segment. Okay, so even if this is this is a whole bar, meaning it does not the cross section does not change, you can treat it the same way. All right, you can break it down into segments and then still do the same thing. Okay, so moving on. Now, what happens when we have an axial member that is tapered, or the cross sectional area will vary continuously along the length of the bar. Okay, so we cannot think to use this equation M5-1. Why? Because it's said to have a uniform cross sectional area all throughout. All right, so how will we go over this? Well, it is just a it's 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 basically the application of this equation M5-2. But how is this an application of equation M5-2? Well, what we can do is that we can isolate into differential segments. Okay, and in these differential segments, where with a length of dx, or differential length of dx, there is a corresponding differential uh, deformation, and the total deformation will be the sum of all the deformations of those uh, differential lengths. All right, so that means that we have, since these are differential strips, we have to use integral calculus. Okay, so uh, based on based on equation M5-1, we make this equation here, equation M5-3, where f is a function of x. That means at any point along x, your force will differ. Well, because again, like the compound axial bar, we have to apply method of sections and expose the internal force, change which will change with respect to the position, because the cross-sectional area grows and grows as we go far away from the reference point. Okay, and the cross-sectional area also is a function of the position. All right, where and we also see that the uh, the modulus of elasticity is constant. Okay, so basically what we're doing is just the play, right? It's F over A times L over E, where L is dx because that is our differential length. Okay. Now, integrating equation M5-3, you will arrive at equation M5-4. Okay, this is integrated from 0 to L. So equation M5-4 applies only to linear elastic material since Hooke's law was assumed, and the equation M5-4 was derived under the assumption that stress distribution was uniformly distributed over every cross-section. Now, the only way that uh, the stress distribution will be uniformly distributed over every cross-section is to make the segments very small, so that stress distribution at this point and stress distribution at this point will most likely be equal. All right, so uh, to solidify our understanding, we will go over a few examples.